Awesome. It's been recorded now. So, hey everyone, thank you so much for making it to the session. This is the first session for a new online community that I'm starting, Quant Finance C++ online. This session is going to be fairly interactive. If you have any, there's going to be a lot of coding in this session. So if you have any questions during the presentation, just feel free to unmute and ask any questions. For the rest of the time, I request you to just keep yourself muted so that there's no background noises. And yeah, let's just get started. So this session is going to be about implementing unique pointer and shared pointer-like container in modern C++. I'll go over first, talk a bit about the community, myself, and then we'll dive right into it. I'll talk a bit about why we need smart pointers, but I expect basic knowledge of C++ and smart pointers for this session. And there's going to be, as I mentioned, a lot of coding. So just feel free to ask any questions while we do that. So let's just get started. Okay, a bit about the community first. So I've started this new meetup community and LinkedIn page, Quant Finance C++ online. If you ever looked at a similar community, there's a Meeting C++ online community, which is basically for all things C++, but it's run online. I took inspiration from that, but this page or this community is going to be focused more on the stuff that happens in Quant and C++ and high frequency trading, because that is where that is the industry I work at. So the goal is to discuss C++ techniques used in Quant Finance, how to get into in this industry and progress in the industry, and make tech and trading a more open and welcoming space. I think there's a lot of usually secrets associated with it, which is not really necessary. So just making it a more open and welcoming space. Before I get started with the session, a bit about me. I'm Sarthak Sehgal. I currently am a tech lead at Maven Securities, a high-frequency trading firm. I joined Maven about 3 years ago in London, but I work in Chicago now. And as you can guess, I'm interested in finance, low-level programming, and C++ under the hood. So let's just get started with the session. So the agenda today is going to be discussing a bit of an overview about smart pointers, but then mainly focusing on how to implement our own unique pointer-like container and a shared pointer-like container. And the primary reason I chose this session to start off Quant Finance C++ sessions was because this really builds a good understanding of how these smart pointers work under the hood. It's a very common interview question as well. If you ever interview for C++ roles, questions like how do smart pointers work under the hood, build your own shared pointer, or how does a stored optional works under the hood are pretty common. And the reason why they're common is that although all these really useful abstractions in modern C++, we still need to have a fundamental understanding of how these work under the hood, because although these abstractions are great, they might come at a performance cost, maybe at runtime or compile time. So it's quite useful to be aware about these costs, especially when you're writing low latency or that's going to run in a high frequency trading environment. So why smart pointers? I assume that everyone's a bit familiar with raw pointers, but what do these smart pointers have an advantage over raw pointers? The first biggest advantage is that they have automatic memory management, which is known as RAII, resource acquisition is initialization. I'll talk a bit about it in the next slide as well. So what I mean by automatic memory management is that it ensures that resources are released whenever the objects go out of scope. So if you have a raw pointer and then you have a bunch of code which might throw an exception, and then at the end you have a delete statement for the raw pointer, then if there's any code between allocating the memory and deleting the pointer, if there's any such code in between that can throw an exception, then you've got this resource which is still there in the memory and you haven't freed up. So that can lead to memory leaks. I'll talk a bit more about it in the next slide with an example. The second advantage is that with smart pointers, you have clear ownership semantics. You have like a unique pointer, which implies that it's a single ownership, a shared pointer, which implies shared ownership. Whereas with raw pointers, you cannot know like whether it's what's the semantic behind it, whether it's single ownership, shared ownership, or there's like other weak pointer. There's other smart pointers as well, but I'll be focusing on unique pointer and shared pointer. And then related to the first point of automatic memory management is exception safety. Whenever an exception is thrown at any code path, it guarantees that the memory is released. So let's understand RAII with an example. So if you look at the code at the bottom, it's on line 3. It's creating an end pointer, allocating some memory on the heap, and then there's some based on some condition. It's returning before the pointer is deleted on line 8. So if this some condition function call returns true, then we're just going to return, and then the pointer is never going to be deleted. This leads to a memory leak. But with RAII, the resource ownership is tied to the object lifetime. So when we do return in this function on line 6, the object lifetime is over. P no longer exists on the stack, but the resource is still there. With RAII aims to solve this problem, and how we can implement. We don't really need smart pointers. We can really implement a very basic RAII wrapper over this pointer. So it will look something like this. The whole idea is that on the destructor, the memory is freed. So if you see line 4, all this container does is add a simple destructor that whenever it's destructed, the memory is freed. And then even if there's, like in the previous example, if we were using this RAII container and we return on line 6, the memory would be automatically freed because the object would be destructed. And we wouldn't need this explicit delete on line 8 because, again, the object would go out of scope and the memory is going to be freed. Smart pointers implement this RAII under the hood. So we'll talk a bit more about that. Yeah, let's just get started with unique pointers. I'll discuss about unique pointer, write a lot of code on how to implement it under the hood. And then we'll see how far we get with shared pointer in today's session. So unique pointer is a smart pointer that owns, that means it's responsible for and manages another object via a pointer and subsequently disposes of that object when it goes out of scope. So this is, again, very similar to RAII, where when the unique pointer goes out of scope, it just automatically releases the memory. The important thing to note about a unique pointer is that it can only be moved, it cannot be copied. So unique pointer is it's the memory that it points to is always owned by a single unique pointer. A unique pointer cannot be copied, so like 2 unique pointers cannot share the ownership of the same resource. It can only be moved. Let me open the CPP ref for unique pointer. So it's I just copied the definition from CPP-ref. You can see unique pointer is a smart pointer that owns blah, blah. But what we're going to do is we're going to look at the class definition of unique pointer. For now, let's just ignore the deleter here. But one thing to note here is that unique pointer has 2 class definitions, which is the first one just takes type T, a deleter type, and defines the unique pointer. But the second one is a specialization for array of type T. So although I won't be talking about the specialization in today's session, it's fairly trivial to go from the first definition to the specialization for arrays. And if I scroll down, CPP reference, it's a pretty good guide to, like, when you're doing things like, oh, how to implement my own similar container or look at what constructors are available. So if I look at the constructors, in this case, there's quite a lot of constructors for unique pointer. We're going to implement a bunch of them. And then there's a destructor operator, equals operator, and then a bunch of modifiers. So release returns a pointer to the managed object and releases the ownership. Reset replaces the managed object. Swap swaps the objects. We're going to be discussing more of these when we start implementing it. Interesting thing to note here is that the array version has all of the all of this stuff, but it also has an extra operator. That is why the specialization is needed. It implements the brackets operator, which provides indexed access to the managed array. So in order to start implementing this unique pointer, I've got a skeleton, like all these definitions in a file already. So let's just start with this and see what we're gonna implement today. So I've got this namespace here called CPP Online, a templated unique pointer class. I've just assigned this alias type name to T star using pointer as T star. You can see in CPP reference, the unique pointer exposes a pointer type. It's a bit more complicated here because they're handling the deleter as well. It's remove reference deleter types pointer if that type exists, otherwise T star. In our case, we don't care about deleter to start off with. So let's just assign it to pointer to type T. Now we've got a constructor, a destructor, a copy constructor, a move constructor, a copy assignment operator, a move assign operator, and then this is some specialization for the constructor where like overloaded constructor specialization is technically not the right term. But this is a constructor when we're constructing using a null pointer, assignment operator using a null pointer. And then we've got a bunch of member functions here, release, swap, operator star access, the pointer access using this operator, and a get, and this is the operator pool where we can check for nullability of the pointer. And then lastly, as we implement once we implement all of these, the next thing which is also interesting to implement is make unique. So if you go to CPP reference, it mentions that yeah, there we go, make unique. So there's a non-member function make unique, which creates a unique pointer that manages a new object. Similarly, there's a non-member function make shared, which creates a shared pointer that manages a shared pointer object. So yeah, let's just get started right into it. Okay, first of all, the constructor. So I already have this data member on line 32 mptr, which is assigned to a null pointer to start off with. So whenever this class is constructed, to begin with, it's always this pointer is always going to be null pointer. So let's start off with the constructor. This constructor takes no arguments. So basically, it should just assign there's no memory being assigned to this unique pointer. So it could just be an empty constructor, does nothing. One thing which I'm missing here actually is a constructor which takes a pointer type. And this is going to be the memory that it's going to point to. So I'll add a constructor which takes a pointer type ptr. And then in this case, all it's going to do is assign this pointer to mptr. Okay, now destructor. Again, remember resource allocation is initialization. And then in the destructor, we want to deallocate this resource. So what we're going to do is first check if mptr exists. If it exists, then simply call the default deleter on mptr. And then assign, this is important because we want to assign the pointer to a null pointer. We don't want to leave a, so if I don't assign it to a null pointer, it's going to be still referring to a memory that I just deleted on line 21. That is called a dangling reference. So we want to make sure that it's not a dangling reference. Like a pretty small nitpick here. On line 20, I check if the pointer exists, and then I delete it. The default deleter actually never deletes null pointers. So it already does a check for only deleting pointers that are non-null. So I can simply replace this with delete mptr, and it should just work fine. Okay, it seems like we've got like a decent pointer running. Let's see. So I've got my namespace CPP online. I've got it's called unique pointer. Let's call it UP1. Actually, I need to give it a key name one. Nice. So so far it does not seem to throw a runtime error. That's good. To visualize it a bit better, let's make this new class noisy foo, and all it's going to do is just make some noise when it's constructing, destructing, and stuff like that. So let's call this CTOR. And then on destruction, noisy foo is CTOR. And let me quickly add some copy constructor and stuff, other stuff as well. So this is going to be copying. Let's copy CTOR. Says okay. So I've got a copy constructor, a move constructor. I think we are good to just start off with these, and let me just include a stream. Okay, everything compiles. So I'll change this int real quick to a noisy foo. And then I'm gonna construct a noisy foo here. By the way, quick check. Can anyone confirm the font size is fine, or is it a bit too small?
It's all good.
Yeah, quite legible.
Awesome, thank you. Yeah, so I just created this noisy foo. You can see it outputs CTOR, DTOR. So that is what we would expect. A unique pointer is created, then it goes out of scope, and the destructor is called. So looks good so far. Looks like our constructor is holding up, and then our destructor is holding up as well. Actually, since I did say that the default deleter is going to handle null pointer just fine, so let's actually create a default constructed pointer and see that it does not throw runtime error. So yeah, you can see this just compiles fine. It's not throwing a runtime error. So should be working fine. Okay. Next one is a copy constructor. So as I mentioned earlier, unique pointers are not copyable. So this is probably the easiest thing to implement. Just equals to delete. That means this is not supported. And then similar for copy assign, I'm just gonna make it equals to delete. So unique pointer is not copyable. Okay, now this is likely the most interesting bit. How does a move operation work in a unique pointer? So moving a unique pointer basically means that let's say you have an object A, then you are moving the A object A pointer to a unique pointer called B. So what it's going to do is remove the ownership from A and transfer this ownership to B. And Chaitanya, I'll just get back to your question. Just give me a second. So if you have a unique pointer A, which you're moving to a unique pointer B, what it's going to do is transfer the ownership of this resource from A to B, and then assign this unique pointer B into a null state. So the pointer that it's holding is going to be null. Objects that are moved from, so like A in this case, should not be accessed after the stood move. So after a stood move, the object A should never be accessed unless you reset it and then re-access it. The ownership will be transferred to B, and A will be left in a reset state. So I've got a question from Chaitanya. Slightly confused as to why an empty unique pointer exists at all. Well, there's definitely a use case, because imagine things like imagine you have a class, whatever. Let's call it a shape container. And then you want to take in some arguments in the shape container. Let's say you're taking in an integer here. And then based on these arguments, you're initializing a unique pointer. So you can have so actually, okay, in this case, you can just construct it during construction. But imagine you don't have these arguments available during constructor in this case. So at a later point, you want to call void construct pointer, pass in an integer. Then you can simply assign this unique pointer to something here. It's not supported right now in the code that I have, but once we complete the implementation, it should be supported. So this case is where you want it to be a null to start off with, and then assign it at a later point, or you start off with assigning this unique pointer something and then reset it at a later point. It's similar to raw pointers. Like, why do we ever want the raw pointer to be null? Because it is possible that at the time of like constructing this pointer, you did not have the resource, but you want to assign it a resource point. You want to assign it a resource at a later point. Does that make sense?
Yeah, this makes sense. Thanks.
Good. Cheers. Okay, so we were at the move constructor. So move constructor is going to transfer the ownership to this object from other. This is the current object. Okay. So in order to transfer the ownership, what do we want to do? So we want to assign the MPTR as the same resource the other object's PTR is pointing to. So what we're going to do is MPTR is other object's PTR. And then I want to assign the other object's pointer to a null pointer. So this is what we want to do. There's a nicer way of doing this where we can use std exchange. So what I can do is mptr std exchange other.mptr null ptr. So what std exchange basically does is assigns null pointer to other.mptr and returns the value of this object before this assignment. This function returns the value of mptr before assignment of null pointer and later assigns it to null pointer. And since this returns whatever it was before the assignment to null pointer, I take that and assign that to mptr. So the initial implementation where what I do is I take the other's pointer, assign it to this like my own pointer, and then assign the other pointer to null is equivalent to using std exchange. So I like this implementation better. It's a very convenient function. So let's just use that, and it's in the utility header. So let's just stick there. Okay. So yeah. So we've got this pointer pointing to the other object's pointer, and also made this important change to to have the other object in a valid state, like we've assigned it null pointer. If you don't do that, it's again important to note that a unique pointer, the whole idea is that only a single unique pointer is owning the resource. Now, if you don't assign this null pointer to the other object, it's still going to be having a reference to the resource that is now owned by this object, which will be invalid. Because what's going to happen is that actually I can probably show that. So let's say that's a bit interesting to see. So let's say we don't assign the other pointer to null for the ownership, but the other objects is still pointing to the same resource. Okay. Any guesses what's going to happen? Actually, let me write a sample code, and I'll try to hide this. Okay, I've got it. So we've got a unique pointer 1 pointing to a noisy foo, a unique pointer 2 and then let's do stood move on. Okay. Any guesses? What's that's because I've got a move constructor, not a move assignment. So let's try to construct it instead of assigning it. Hopefully it compiles. Yeah, there we go. Okay, so there is a problem with this code because I haven't assigned the other pointer to null pointer. 10 seconds for if anyone wants to guess what the problem with this code is.
Double free, basically. The same resource will be free twice, which is, yeah, basically the whole program will crash.
Yes, exactly. Thanks. That's exactly the issue. You can see here it prints free, double free detected in Tcache too. So what's happening here now is that on line 67, I create this noisy foo object, assign this resource to my unique pointer 1, and then I move construct this unique pointer 2 with up1. But now both the unique pointers have this pointer pointing to the same resource, like the same resource I created here. Now, if you notice in the destructor, all we are doing is if this is non-null, this is going to be destructed. The pointer is going to be destructed. So now both my first unique pointer and the second unique pointer, up1 and up2, have a valid pointer pointing to a resource, and then they're going to end up deleting it twice. So because I'm compiling with like GCC, it's not optimized compilation. It's just gonna actually this is this is a runtime error, so not exactly due to me compiling it at a lower level. But yeah, here GCC just is able to detect a double free error. Now let me quickly change it to state exchange, and we'll see that it all just works fine. Okay, so this is what we'd expect: CTOR, DTOR. Okay, now that we've got the move constructor up, the move assignment operator is pretty similar. Again, all it does is pass on the ownership. The one important thing is that this is a move assignment, not a construction. So that means that the current object, like this object, also contains a valid state. So we want to reset that valid state before we transfer the ownership of the other object to this object. So what we want to do is delete the pointer first, and then assign the, like this is because, my bad. This might be holding some state, some resource. And then we want to do the same thing as move construction, where we call state exchange. That's it. So it's a bit different to move construction, where we are freeing the resources that it may already contain. I'll give an example of like how it tests for this a bit later, the move assignment. Okay, the next one is the constructor using null pointer. This is a fairly trivial one. We already have a null pointer here, so we're just gonna default construct it. You could also use like a delegated constructor where you're default constructing it, but this works just fine in our case. Next is an assignment operator to a null pointer type. Again, a bit different because the object might be containing some state. So we should first free up that state and then assign the pointer to null. So the only difference is just delete it and then assign it to null pointer. All right, we are getting there. We're almost there. Let's just do the simple ones first. So all this all the operator bool checks is for the it checks that the pointer is not null. So this is pretty simple. And pointer is not equals to null pointer. All the get method does is return the pointer. So this is pretty simple as well. simply return the pointer. This operator is equivalent to calling get. So let's just call get. And then the dereferencing operator returns a reference to my pointer. The important thing to note here is that this dereferencing operator is unsafe in the sense that it does not check that the pointer is null and like would return you a different value depending upon whether it's null or not. So you need to ensure that when you're dereferencing a pointer, it does contain a valid resource. That is, it's not null. It's similar to, the behavior is similar to raw pointers. Okay, so now all we've got left is release and swap. Let's see what release was doing. So release returns a pointer to the managed object and releases the ownership. Okay, so if you're writing, the reason release exists is likely for like backwards compatibility. If you have some class that is taking a raw pointer, and it's guaranteed that once you convert this unique pointer into a raw pointer, it's up to the client, up to the user to manage the ownership and everything else, the resource management of the pointer. Then you can use release. So it's basically returns you, like it basically frees this unique pointer class of any resource management, but keeps the memory alive and returns you a pointer to that memory. So if you have some old style C code, you can still use the raw pointer. So what it's gonna do is it's gonna return MPTR, but also assign it to null pointer before it returns it to ensure that there's no double freeing. So what we can do is again use to exchange and exchange it with null pointer. So what it does is assigns the current class's pointer to null pointer and then returns a pointer to whatever the class previously contained. Okay, so all we've left with is swap. Swaps the current pointer with an incoming unique pointer. Pretty simple stuff. All we need to do is call should swap on MPTR with others pointer. And that's it. We should be done with the unique pointer implementation. I've got a bunch of sample tests. Let me just pull them up and see everything passes. Do I need to see a cert here? Okay, warning, no return statement. That's a good one. So we're missing a return. For this, you can see the assignment operator returns a reference to the current pointer. So we need to make sure we're returning a reference. And similarly here, we need to return a reference. Okay, so we haven't implemented make unique yet. So let's just comment this out for now. Okay, so I've got a bunch of test cases here. First one, just default constructs a unique pointer, and then it asserts that unique pointer returns false. So we implemented the Boolean operator. It returns true if the pointer is managing some resource. In this case, it's not managing a resource, so it returns false. Then I assign this to a unique pointer pointing to this new resource pointing to 1. And this kind of delves into the question Chaitanya asked earlier, that why do we need to have the default constructor at all? So we can have cases where we still want to default construct it, but assign it at a later point, similar to this test case. So once I've assigned it to a pointer pointing to a memory resource which contains this integer 1, I've asserted that that's equal to 1. In this assertion, I'm also using the dereferencing operator. So that seems to work fine. And then another important thing to note is that the dereferencing operator returns an L value, which can be updated. So I then updated it to 2 and asserted that it's equal to 2. That passes as well. And then I created a new unique pointer, asserted that the value is the same as I expect. And then this is a test for move assignment. So in this case, it's not a move construction. Previously, I showed you move construction. Now this is move assignment. You can see that the pointer 1 is moved to pointer 2. Then we would expect that the pointer 1 is null and pointer 2 has the value that was there in pointer 1. So pointer 2 previously had 3. Now it's got 2, which was there in pointer 1. So yeah, it seems like our unique pointer looks pretty decent. Before I move on to make unique, I'll break for if there's any questions so far. All right, if no questions, I'll move on to make unique. So you can see there's a lot of templates here. I'll give a quick overview of what these templates do. Won't delve into too much details. Basically, what you've already seen, type name T, it's just makes this class, like in this case, a function makes this function generic with any type T. Then we've got this type name ... which might be any syntax for some people. So what this is called is a variadic template parameter pack, I believe, but like basically variadic templates in C++. So this implies that there can be any number of arguments args here, even non-zero. So this would take 0 or more types, and then the function basically returns a unique pointer to type T, and then takes in all these arguments, 0 or more. So we'll be able to call make unique with 0 or more arguments. Basically, that's what this does. So what make unique does is the whole point of make unique is that you'll know as like soon when I show an example. But let's compare line 121 with a line 114. So in this line, I'm creating a unique pointer, but I have to call this new int 3. Like I have to give it the exact type integer for a unique pointer of type int. And then I have to allocate this resource in my code, and then construct the unique pointer with a pointer to whatever this resource I allocated. But on line 121, all I'm doing is calling a make unique integer 1, and then simply passing the integer. So I'm not calling new int. I'm not creating a pointer here. I'm just simply passing an integer. So make unique basically abstracts this resource allocation from us and does it inside the function itself. So you don't have to do this each time. Okay, so make unique, in case of unique pointer, it's a pretty simple implementation. All we want is like we want a unique pointer of type T. We want to return this, and all we want to do is call new T. Then these arguments, I'll just write the syntax. Like this is just some like C++ syntax, doesn't matter. Not the purpose of this session is not to focus on templates. So actually, this is not forward. It's forward. So yeah, this is the syntax to forward a bunch of arguments that you get in the function. But I won't get into too much details of that. So yeah, all it does is abstract this resource allocation away from the user. So now we can simply call make unique int1 and then assert that. Oh no, so doesn't have to be stood. That's my bad. It has to be our pointer, not the std pointer. Yeah, there we go. So created a new unique pointer and then asserted that the unique pointer is equal to, that the value is equal to 1. That's it. It's more useful when we do make shared. I'll talk a bit more about it when we implement the shared pointer. Now, before I move on to the shared pointer, I want to pause for any questions. Okay, if no questions, I've got the links to the implementation here without the deleter and with the deleter. Having looked at the time, I think we are almost running out of time. So instead of going to the shared pointer, I'll go with the implementation for a unique pointer with the deleter pointer in our next session. Have a look at the deleter. So if I go back to the unique pointers CPP reference page, I initially pointed out that unique pointer takes a template type T and also allows the user to pass a custom deleter. So there are cases when you want to hold the type T, but then have it delete, like have your own custom deleter to free up the resource. Now let me give you a classic example for this. So I've got this running. Let me remove all this stuff. Oh, okay. I've got hash include memory. So let's create a unique pointer. Now the important thing to note here is that I'm using the standard library here for the just to show you an example. So I've got a unique pointer of type int up and then new int 1. It's not assignable to pointer of type p star. It's constructible from it. Okay, this works well. We've seen this pretty simple example. But let's say you want to store a unique pointer to void. Now there are barely any good reasons to do this, but let's say you have some code which depends on some fancy technique like type erasure or something, and you want to store a unique pointer of type void. Now, if you try to do this, you will see that it won't even compile. So this is a compilation error, compiler stood error. And the compiler has the static error, not is void value. Now, open to the room, any guesses on why this doesn't compile? Like, what exactly is the piece of code that fails when we try to create a unique pointer of type void and assign it a pointer of type int? And if this is doable with raw pointers, by the way. So if I have a raw pointer, then I can assign it an int pointer here. So just to clarify, this will compile, but this doesn't. Any guesses on what code breaks?
The deletion part, because now you don't know the type of the object, so you can't delete it.
Yes, exactly. So in our destructor, if I can find it, yeah, in our destructor we are deleting the pointer, but now this pointer points to this pointer is a pointer to void. To delete the resource correctly, we want to know what the type of the resource is, and deletion, the default deleter does not allow the pointer to be void to be deleted. So what this static assert here is doing, again, this is a check at the compile time, not at the runtime. So this code doesn't even compile. So the static assert is basically asserting that the pointer type is not void when the default deleter is called. So let's forget about unique pointers for now, but let's come back to raw pointers. Now, at somewhere in our code, we had this raw pointer, but we assigned it to a void pointer. The reason you might want to do this are in some techniques that we still use void pointers. Like type erasure is a technique in C++, where you erase the type of the object, but still assign it to a pointer. So now void pointer can be assigned to basically anything else as well. So you could you could really assign it to a double at a later point, and that's the advantage of a void pointer. If this were a pointer to type int, then this wouldn't be possible. But although this brings like a lot of possibilities, it also brings a challenge. How do you free up this memory correctly? And to do that, what we can do is okay. So in the case of unique pointer, we can pass it a custom destructor, a custom deleter. So if I go back to unique pointer, it accepts two arguments, a type T, a deleter. It defaults to std default of type T, which we know in the case of void is not valid. But what we can do is, when we are assigning it an integer, we know what the type is. So we can do auto my int deleter. I'm creating a lambda function here. It takes in a void pointer, casts it into an int pointer, casts it in an int pointer, and calls the default deleter on it. So I have this deleter which takes in a void pointer, casts it into an int pointer, and calls delete on it. Now I'm going to take deca type basically takes the type of whatever you pass into it. I'm going to take the type of it, and now it compiles. To prove that it runs fine, actually, let's use noisy foo instead of new int. Let's call this noisy foo. Static cast it to noisy foo pointer. Void pointer static cast it to noisy foo. Yeah, this should just work fine. Yeah, so you can see now it calls the constructor and the destructor. So it works as expected. So the whole point being that you can pass a custom deleter to unique pointer when you're not necessarily managing the type T. So there's a type name argument T, and then there's the object that you're managing. It's also useful when you're using inheritance hierarchy. Imagine the type T being a base class, and the object that you're actually passing it being a derived class. So in that case, although the type T is a base class, you want to destruct the object type, not the base class type. So it's quite useful when you're using inheritance hierarchies as well. So let me quickly find if I have the code with the deleter on there. There we go. It's not. I'll have the link on the slide so you can have a closer look when you get a chance. But most of the code is pretty similar. We've got the deleter here defaulted to default delete. Then it's got a constructor which takes in the pointer p, constructs the pointer with the incoming pointer. The move constructor is a bit different, wherein this is the same. It assigns the pointer and then moves from the incoming object u, assigns null pointer to the other object. The deleter, it simply moves the deleter, calls should move on the deleter, and move constructs the deleter of the current class. The interesting bit is the destructor, where now instead of calling default delete here, it just calls the deleter with our pointer and then assigns our pointer a null. And then the class just throws the deleter. Yeah, that's it. I mean, implementing a deleter, extending it to a custom deleter is pretty straightforward. It's just a bunch of more boilerplate code that's needed. I've got it on the slide so you can have a look. But yeah, I don't think we've got enough time for the shared pointer. I'll discuss that in the next session. The shared pointer is much more interesting, I think. But usually when it's to build up to a shared pointer, it's necessary to understand how a unique pointer actually works. So it's it's quite important to implement a unique pointer before you implement a shared pointer. Also, both of these are like pretty common interview questions, especially in the quant finance and trading industry. So it's quite useful to just crack down on both of them. So if you have any questions, I'm happy to answer them. If you have any feedback about the session, please just scan this QR code and send in your feedback. I'd really appreciate it. It'll help me plan out for next sessions. You can like submit some ideas if you have about upcoming sessions, what you want to see, and stuff like that, and give any feedback. Yeah. Happy to answer any questions.
Quick question. Do we need to use custom deleters if we are using, if we are not using new and delete, say malloc and free?
So your voice was breaking a bit. Your question is, do we need to use custom deleters if
we are using malloc free, for example, or any other type of custom memory allocator?
I'm so sorry, Chaitanya. I didn't get your question. It's quite fuzzy, the voice for me. Do you mind typing it out, or we can take it over the chat? All right, thank you. Okay, as Chaitanya writes, types the question. Just a quick note about what's planned next for the community. So I think like my goal is to have a couple of people from different firms as well on here sharing their experiences, different profiles. I do low latency trading software at Maven, but there are a bunch of other profiles as well. There's a lot of data analysis and Python, and then platform teams. So goal is to bring a couple of speakers as the community grows, but also continue doing these sessions on niche techniques, C++ fundamentals, and like examples could be implementing lock-free queue. Again, this is like a very this is a bit more advanced question, but it's a very important and very common question on how to implement your own lock-free queues using Stud Atomic, Stud optional, as I mentioned before. If you like the session, please follow the page on LinkedIn and help spread the word. And as I mentioned previously, any feedback would be greatly appreciated. So I'll get back. So the question is, do we need to use custom deleter if we are using malloc or free? So in unique pointer, let me get back to this. So you can see that it's not up to you to use like it's the unique pointer abstracts away the object construction and deletion. So when you say if you are using malloc or free, you can see that the like I guess you can construct it here. You can construct using a malloc, but the unique pointer is going to be destructing it in its destructor. The whole point is that this unique pointer class is now responsible for destructing this this resource correctly. So you can see that in the code, you would never call free or delete or any of the other stuff. It would just take the type T of actually this type T, the type you pass it in the class, and call a deleter for that type. Does that? I'm not sure if that answers your question, Chaitanya. The point being that it's not the user that's calling free or delete. It's the unique pointer class. And yeah, so in this case, if the object you're passing to a unique pointer matches the type of the class you're constructing, you don't need to pass in a custom deleter. Because if you again go back to the class definition, the custom deleter has a default for deleting the type T. So in this case, you don't need to pass a custom deleter. For example, I'm not passing one here. But if for any reason these two types, the object type and the class template type, do not match, then you should be passing a custom deleter. And this can happen because you can have like a base class, derived class hierarchy you're storing an object of derived class, but you want to store it as a reference to the base class. So you want to delete the object correctly, or like in the example of void pointer that I mentioned. I'm not sure if this will work, but just for the sake of example, let's say I've got a pointer to double. Oh, because it expects a pointer to T star, the constructor. Yeah, this won't work. But yeah, I guess my point being, if these two types match, then no need for a custom deleter. It's gonna default it. But if they don't match, then you do need a custom deleter. Does that answer your question, Chaitanya?
Yes, please.
Okay, great. All right, if there's no other questions, thank you so much for joining. And I hope that you fill the feedback. And I'll see you in the next session, probably planned for 2 weeks from now. That's the goal. So yeah, thank you so much, everyone.